Okay, thanks for the introduction. And so today I'm going to be talking about a few different topics around language and generalization. So as Elijah pointed out, I have this recent blog post I call "Just Ask for Generalization," and then I'm also going to share a bit of you know work in progress material that I'm working on, where I argue that language and generalization might actually be the same thing, and then applying these kind of ideas to a real-world robotics problem. So when we talk about generalization and machine learning as practitioners, there's a very common setup where you have some data and then you kind of split randomly some of the data as training data and some of the data as test data. And what we think about as generalization is like how well it does on the unseen test data once you train your model on the training data. So this is kind of a casual practitioner's understanding of generalization. And so formally, there's some tools like generalization gap, uniform stability, VC dimension, Rademacher complexity, pack-based, kernel methods, and so forth to understand generalization in a more formal mathematical context. But despite significant effort and many recent advances in generalization theory, it's still our understanding of generalization in large overparameterized models like deep learning still lags behind a lot of the empirical results. And the sad fact of the matter is that what governs generalization is still very much a matter of debate in the research community. So we really have no idea what's going on. Here's one of these weird things that happen in deep learning, as some of you may be aware. So when you train a large deep neural network on training data, training loss goes to near zero. And at some point, you would expect that the overfitting causes test losses to go up, like this parabola here. But with deep nets, after you train for even longer, it will somehow go to this modern interpolating regime where the test loss starts to go back down. And this is kind of counter to our classical intuitions of how overfitting and generalization work. And this is called like double descent. So instead of talking about what the kind of formal definitions of generalization, I'm going to illustrate some qualitative examples of what deep nets can generalize to. So there's a data set called ImageNet that contains a lot of natural images. And in an attempt to study how robust these models are trained on this data set to other augmentations, there's this data set called ImageNet corrupted, which adds like different kinds of noise, Gaussian noise, shot noise, impulse noise, and so forth to the images and sees how well can you generalize to these unseen kinds of images. And you quickly devolve into this sort of semantic hell where you start wondering whether like a model should or should not understand these images, given that it's never seen these before. I mean, we all know that we can see these are birds, but if a model hasn't been trained on them, like, should it recognize them or should it not? And these kind of questions become a little tricky. The authors of this paper kind of sidestep that question and just focus on what is the performance on these corruptions as a metric for understanding like how well models can generalize to some kinds of noise. There's a recent result in 2019 by OpenAI called GPT-3 that is very popular in the media, where they showed that if you train a large language model to just predict the next word in a sentence, this model can do a lot of really cool capabilities. And so one of the really cool things it can do is that you can prompt it with a new natural language task and maybe give it an example as well as to help it along, and it'll be able to do the task. So even though the model is just trained for next word prediction, by giving a little bit of prompt engineering, you can get it to perform translation, you can get it to solve math puzzles and play chess and so forth. Here's one of my favorite examples of generalization. So here is a model that's been jointly trained on internet data of images and text. And you can ask it to generate images that it's never seen before in the training data. So by conditioning on natural language. So you can ask it for a picture of a baby panda with headphones staring at its reflection in the mirror. And there's no image in the training data, to my knowledge, of this specific kind of image, but the model understands how to put together like the panda and the mirror and make the image coherent enough that you can actually see the reflection of the panda in the mirror. And so this is quite impressive in terms of being able to compose distinct concepts in separate parts of the training data. Oh, and by the way, if I'm speaking too fast or if something I'm saying doesn't make a lot of sense, feel free to interrupt me. Think about this like an interactive discussion. But here's another example. Here's a banana performing stand-up comedy, and the network does something kind of reasonable. It draws like the this standard comedian blue jeans on a stage and a banana with a microphone. So it's quite impressive. So the question I want to pose is that given that we've seen so many exciting capabilities of generalization in machine learning, how much of the other stuff that we do in ML research can we offload to this magical deep neural network generalization? And I'm going to go through a few examples in both generative modeling as well as reinforcement learning. So circa 2014 to 2018, many researchers who worked in modeling computer vision images, like the faces data sets, would notice that your generative model either does a lot of mode dropping, like if you're training a GAN, it would produce very non-diverse set of outputs, although they might be pretty crisp. Or if you're training something like a variational autoencoder, it would cover the modes better, but the images would be all blurry like this. And this is a problem that a lot of people had a lot of armchair debates about in the research community of like, what's the mathematical reason why these images are so blurry? Is it because our variational lower bound is not tight enough? Is it because what is it about GANs that VAEs don't have, and so forth? So today, people can use prompt engineering to just tell the model to generate a sharp image. And so there's a name for this called the Unreal Engine trick, where if you have a language condition generative model, you just tell it, angel of air feature Unreal Engine, and you append this Unreal Engine string to like any prompt, it'll give you really sharp images. And so this reminds me of this IQ bell curve meme where, the kind of person who overthinks it thinks that GANs need some sort of mathematical, or GANs and VAEs need some sort of mathematical formalism to get you better images. But at the end of the day, you just tell the model to make pretty images and it'll do it. And that's kind of where we are today, I think, in a lot of large scale models. And that potentially has a lot of exciting implications for how we design algorithms. So I'm going to switch over to reinforcement learning. So in reinforcement learning, it's classically thought about as a usually discrete decision-making process where you have an agent, and the agent gets observations or states from the environment. It emits some action, and then the environment hands back a new state, which is like the new state of the world that the agent arrived in, as well as the reward it got for taking that action. And the goal of reinforcement learning algorithms is to have the agent collect some data and maximize the return from the environment, return being the sum of the rewards in the environment. So for people who have ever trained an RL algorithm like DQN or PPO or any of the variants like this, you'll know that reinforcement learning is generally harder than supervised learning to train for a variety of reasons. And the biggest one is that not only are you trying to learn from a large amount of data, but you also have to decide what data to collect as well. So you're trying to solve two problems at the same time, and these problems strongly influence each other. Two popular families of algorithms in reinforcement learning are policy gradients and approximate dynamic programming. So with policy gradients, the idea is that you collect some data with the best policy you have so far. Then you use some sort of black box gradient estimation technique to compute the gradient of your environment return with respect to your policy parameters. And your environment's not necessarily like a differentiable thing, so you have to stochastically estimate this. So you collect some data, you estimate the gradient, then you update your parameters, and you repeat. And this is a simple approach called policy gradients, and there's a lot of modern formulations like PPO and actor critic. The other approach comes from tabular environments, like for example, backgammon a few decades ago, where you have like a value function of the optimal policy, which tells you, well, you start with learning value functions, which tells you like, given this current state, what's the expected return I'm going to get if I, continue with the current policy. And it turns out you can use dynamic programming to stitch together suboptimal trajectories. So for example, if like there's one part of the trajectory that finished the task, but and started in the right place, and another part of the trajectory that got you to that place, then you can kind of bridge these two trajectories together to give you the optimal trajectory. And so these algorithms include DQN, QTOpt, actor critic, and DQN was like the famous 2014 paper by DeepMind that played a lot of Atari games. So these RL algorithms, they give you the ability to optimize for a good policy, and these policies can even do better than any data you've experienced so far, which is a really nice property because that means that RL agents can get better by themselves. But this property is achieved by construction, right? So in the case of policy gradient, you you build a estimator for the return function. And then in the case of approximate dynamic programming, you are trying to bridge and stitch together trajectories that are coming from different policies. So this property of getting better than your data is achieved by construction and not by generalization. So the reason why I think that RL can be kind of limiting as an optimizer is that they're empirically worse at generalizing than supervised learning. So my blog post has a sketch of a proof of why this is the case, but I'll kind of just give the intuition of why this is. And also empirically, there's this recent review that kind of surveys different kinds of generalization we see in game environments and robotics, and like if you just read these kind of case studies, it's just a lot less generalization than what we see in training perception models or autonomous vehicles perception stacks. So the kind of high level idea of why reinforcement learning is sort of a worse optimizer than supervised learning is that you need to do a lot more work to get the same gradient information. So for example, if you're training a robot to do different things and your robot either does it or doesn't, and so you have a binary success signal, in order to estimate like a policy gradient to get within some sort of confidence interval of, let's say, 2% improvement at 99% confidence interval, you need to gather like 4,000 examples and that's just for one task. And many people in who study like artificial general intelligence or robotics want to build robots that do many tasks. So for each task you need like 4,000 examples, and that's just like the gradient for one task. And if you want to estimate gradients for many tasks, then you have to gather quite a lot of data for just the current policy, and then repeat this every time you want to take a step. So there's this kind of sample complexity problem with collecting sufficient data to estimate the direction of improvement. And I think there's also like a philosophical problem that arises from trying to learn policy or compute policy gradients for general purpose systems. So if you imagine like a general purpose robot that can do, I don't know, 1 million different tasks, what does it mean to like compute a policy gradient that makes it better at 1 million tasks? It's well, it would be very expensive to compute like the gradient for all 1 million tasks. So maybe you can use a subset of them. But if you're taking only the policy gradient for a subset of tasks, then it's only really going to guarantee that you get better at those tasks and not the other ones. It could very well forget the other tasks if it wants to. So my hope is that we can just focus on generalization. That's the first class citizen. We minimize empirical risk with the tried and true tools of supervised learning. And then after the fact, we just ask the policy to be optimal via some sort of conditioning variable. So I'm going to cover a few related works that kind of get at this idea and show the promise of this framework of thinking. So there's a recent paper called Decision Transformer, which gets state-of-the-art performance in offline reinforcement learning. And what that means is that you just start with some data, and then you train the algorithm on it without interacting with the real environment, and then you deploy the policy and see how good it is. So the idea is that like you have a sequence of tokens that represent your state observations, your previous actions, and your previous return to go. And return to go is just the return remaining in the episode. So if you collect some episode and it gets like a series of rewards like 1, 2, 3, then your return to go would be 6, 5, 3. I'm sorry, no, 6, 3, 1. Yeah, that's the return to go. Right. So you train a model to just like take in the sequences and emit the actions. Given the outcome of the episode, you kind of pass it back as a conditioning variable for what you want the model to achieve. And then turns out this actually achieves state-of-the-art performance in many offline benchmarks. So you don't have to use RL. If you think about the return to go as like a sort of hindsight conditioning variable that you tell as a goal for the policy, a richer version of this would be just to describe some sort of language of what happened, right? Instead of a single scalar of like return to go, you're providing hindsight labels of what happened in the episode. And so some work from my colleagues at Google learned this very cool system where you could have a robot explore like a baby in the simulated scene. Then you relabel the trajectories with what happened. Then you train a model to take in what happened and what it's looking at, and it produces the behavior that realizes that description. And you can get the robot to do many cool things in simulation. And so I think of like hindsight labeling with language as a generalization of this idea of relabeling what happened as a goal. So a lot of people in reinforcement learning also think about RL as a way to improve behavior beyond, incrementally. But I think of learning as more of a behavior rather than like a hard-coded algorithm that you use to get better behaviors. So in an abstract sense, like if you think of a robot that's getting better, what you really want is a function that takes your current set of parameters or policy or whatever, and some experience, which I've denoted as tau here, and it just maps that to a better set of parameters or an improved policy. And so why not learn that function with a neural network? And so in 2019, some collaborators and I built an algorithm that just trains a policy improvement operator using supervised learning. So you have a episode which is like a video of this floating gripper trying to do some task, and then the current set of parameters, and the function takes in the policy and the experience, and it just outputs a better policy. And we just train this using supervised learning, because if you have a distribution of policies, you can just map worse ones to better ones. And it turns out this function generalizes, and you can use this at test time to rapidly improve and solve tasks if it gets it wrong. And we do this all with supervised learning as opposed to using reinforcement learning tricks. So to summarize this kind of framework for solving problems, the recipe is quite simple. You first choose a method capable of training on a lot of data, like as a data sponge, you can absorb everything. So you want to minimize empirical risk. Supervised learning is a great choice for this. Unsupervised learning also seems to work well. And even reinforcement learning is fine, but you just want to make sure that you're not using any inductive biases that cripple the ability for your model to overfit quickly to data. And then, once you get overfitting, then you start to get really nice generalization. Instead of modeling a single policy or trying to optimize a single policy to be the best one, maybe you just model everything and then you just ask the neural network to give you the best one. And this is leveraging generalization rather than an optimization by construction. And finally, I think natural language is a good way to formulate the conditioning variables that help partition your data distribution. And I'll talk a little bit of why this is actually the best interface. But we've seen from past work that natural language is an ideal interface for capturing all sorts of meaning and outcomes in very unstructured data sets. So here's a few random ideas just to toss out there in this flavor. I'm not aware of any work that kind of like executes this really well, but you can imagine as compute and the size of our GPUs gets bigger in the future, these things actually might start to become quite plausible to implement. So a very hard problem in reinforcement learning and also language modeling is getting long-term memory to work. And you can imagine training a policy with a certain amount of memory capacity, but then at test time, you just ask it for more capacity. And maybe the model will understand what it means to have memory capacity in a sort of a sliding capacity sense. So you can ask it for a small amount of memory or a large amount of memory. And at test time, you ask it for even more memory than what it's been trained on. And maybe it'll extrapolate and do something reasonable. In a similar vein, exploration is a hard problem in reinforcement learning. So maybe you can just ask it to explore more. And if you have a policy that knows what it means to explore more, from in terms of understanding English, you can just tell it to explore more, and you don't have to write down fancy entropy maximization algorithms that people use in reinforcement learning. Here's another idea. Imagine when we train reinforcement learning algorithms, we often have to wait quite a long time for the model to converge. So why not just ask a model to converge, right? If you've trained enough models, in a sort of a meta sense, a human researcher knows how to look at a performance curve and kind of guesstimate when something's going to converge. So you can imagine that intuition from the researcher being distilled into some sort of network that can guesstimate what the converged behavior of a series of policies looks like. And then, going even further, imagine you have a model that just reads the LaTeX of some paper and then spits out the outcome of what happens if you were to implement the algorithm from the paper. And maybe that would work someday as well with sufficient compute. So now this is a very highly speculative thing. I have no idea if this is true, but just food for thought. If you have models that can understand, the kind of fuzzy specification that is language, what if you can just ask for pretty advanced things like consciousness that we have trouble defining? So here's one way you might do it. You train two models that can capture many different policies and model many different agents. For example, let's call them like pi A, pi B. So you first train the policies to be able to imitate a variety of agents, right? And this is the first bullet point, which is like metacognition of other agents in the world. So if your policy is able to model many different agents, also it's interacting with the world, it kind of understands how other agents think in some sense. And then at test time, you can just ask it to behave like any other agent, and if it's able to do this, then it demonstrates that it can perform some sort of metacognition ability. So now we attach a special token like you and say like, behave as yourself. And there's some sort of like stereotypical behavior here that is not like the other behaving like the other agents. So then now if you have two such models, maybe you could ask a model to behave as another model imitating yourself. And if the language conditioning all works out, then my hypothesis is that if you're able to perceive yourself through the distorted perception of other agents that are trying to imitate you, then this is sort of a precursor to theory of mind and maybe even subjective qualia, because you have to represent the concept of yourself transformed in many different ways. And you can think of those transformations as like data augmentation that forces a more robust representation of the self. And I'm sure like there'll be a lot of questions on this end, so I'm happy to delve into this later if you want more clarification on this. Okay, so I'm going to move on to the next part of the talk, talking about like language and generalization. So returning back to like the more practical considerations of how to make generalization work. I previously said that like theory in generalization is quite detached from practical intuitions of generalization. So even though we can define things like generalization gap, it's still pretty hard to answer the very practical question of, given my training set and I train a model on it, how much generalization can I expect from the model? For example, like let's say I'm doing some data science at Stitch Fix and I'm training like a generative model for making clothes or something, and if I train on some jackets and then some denim jeans, could I expect it to give me some denim jackets? Like who knows, right? This is like beyond the understanding of theory of generalization, and in practice, what people just have is like an intuition of what it takes to get a certain amount of generalization. And this is, I think, not too obvious to researchers, even in who study this stuff in the field. But there's a few kind of questions that people think about in machine learning. They're actually equivalent to this question of like how much generalization can you expect. So when people talk about like what is in or out of distribution, that's the same question. When people talk about whether something is robust to adversarial examples, it's also the same question. And then also like when people talk about uncertainty and stuff in models, like how can you get models to know what they don't know? I also believe that this is equivalent to the question of like how much generalization can you expect. And I think like the community has not caught on that like it's sort of like the blind people feeling up the elephant. Everyone's seeing it from a different angle, but at the end of the day, like the kind of hard practical question is, given your data set and your model, what can you expect it to generalize to? And what even is generalization, right? Like that's kind of a slippery concept to define. So when people talk about generalization, they often really mean like they want the AI to be smart, and generalization is kind of like this catch-all term for describing AI systems that are working well but trained using machine learning. And there's this grab bag of capabilities. So just to list a few, like invariance is one example. So if I train a cat classifier and I show you like a cat you've never seen before, it should be recognized as a semantically equivalent concept to something that I've seen before in the training set, even though that specific set of pixels I've never seen. So it's like you can think about continuous signals of like image space or very high dimensional signals that vary a lot, projecting to the same discrete concept that is a cat. And the other side of this coin is like robustness, right? So small variation in the input, let's say I've sprinkled a little bit of noise, it should still be semantically equivalent to a cat, the same discrete concept. Another thing that people want when they want AI models to generalize is to, let me close some chat window. Yeah, so another thing when people want, when they talk about generalization is like some sort of common sense reasoning. So the outputs of your model should be sensible under some general understanding of the world. And there's different names for what people call these, like intuitive physics or causality and so forth. There's also extrapolation. So a common example of this is like if I'm training a machine learning model to add numbers, and I train it on numbers like integers between, let's say, -100 and 100, the model should generalize beyond the numbers 100 as well. That's the intuition of what extrapolation means. Or another one would be like maybe I'm testing on high contrast images, but my training data set is only low contrast images. And if a human can kind of handle this training task, then maybe so should an AI. But these are kind of spread out all over the place. And what people really mean when they say generalization is that the ML trained system is smart. So there's a recent paper by Hupks et al. 2020, and they have a really nice way to decompose the compositionality in language. So they're interested in generalization, and they kind of define generalization as this nature of like compositionality in language. And they have these 5 elements: systematicity, productivity, substantivity, localism, and overgeneralization. So their paper focuses on evaluating like language understanding models in the context of these 5 sort of testing areas. And so systematicity is like being able to compose words that haven't occurred together in sentences before. So for example, if I said like Bob went to school and Sally ate lunch, it should also understand like Bob ate lunch, right? Like it's able to put 2 concepts together. Productivity is being able to combine sentences into longer ones, and this is a little bit kind of like extrapolation. So even though you might have been only trained on sentences of length 2 and length 3, it can also work with sentences of length 5. Substantivity is this idea of the cat being invariant. So for example, if it sees like a synonym of a word like school and university, it should still understand the meaning is it has not changed. Localism is when you have sort of local rules being applied before global rules. And I'll give an example of a non-language context later, but one example for language would be like if you're parsing code, maybe you want to evaluate parentheses in terms of order of operations first before you evaluate something outside of those parentheses. And then overgeneralization is the ability to handle exceptions. So for example, if there's some sort of conjugation in Spanish that has some exception to the word, it's not going to be biased by all the other cases in the data set that follow the common conjugation pattern. So these categorizations actually work in other domains, and there's a recent nice paper studying this categorization of generalization for reinforcement learning agents. They look at basically these systematicity, productivity, and so on in the context of RL agents, and they develop analogs for like what it means for these concepts in RL. And so just to give a few examples of like these things applied to non-verbal situations. Imagine you have like a household robot, right? And that robot's able to pick up the cup and push the bowl, and then that's the task it was trained on. You would expect that it should also understand how to push the cup. That would be an example of like good generalization in a robot system. Extrapolation or productivity is like maybe you can handle longer commands or embed predicates inside of other, embed clauses inside of other clauses and handle longer instructions, even though it's trained on shorter ones. Substantivity is very simple in like visual perception. The robot has to understand that like 2 cups mean cup. Localism would be something like intuitive physics. So you would understand that like local physics kind of give rise to long-term results, and there's no kind of spooky action at a distance when you're thinking about how to model videos or something. And overgeneralization, let's say your robot's kind of operating in the wild, and when it's in Japan, they stand on the left side of the escalator when they're riding up the escalator, unless you're in Osaka and they stand on the right side. And so that's an example of where you would want a system to be able to not overgeneralize. So the point I'd like to suggest here is that if you can apply this categorization to study generalization in RL or robotics and other nonverbal situations, maybe the ontology of language described in this paper here, or in terms of like what properties you want when a language model generalizes, is actually the same ontology for generalization in other nonverbal domains. Therefore, the ontology of generalization is the same as the ontology of language. Like these properties are just properties of language, right? So if you buy that argument, then maybe if we want our systems to generalize really well, what we want to do is just take, things that understand language, for example, and the best thing we have right now is like these large language models that are trained on internet scale data. Things that, roughly understand language are proxies for things that understand generalization in all the various forms that we want. And you can bolt this on into nonverbal systems like robots and get them to generalize better. So here's a simple architectural diagram of some images that go into a very shallow perception stack. They make word embeddings, and I don't mean actual words, but like, tokens that represent what's in the image, but not even like semantic meaning, just extracting some tokens from the image, right? Then you have this large language model that acts as a sort of generalization module that does all the thinking for the robot, and then it outputs some words, and then you decode them into the actual predictions like actions or something for the robot. And I think if what I said is true, then we'll probably see a lot more cool architectures like this in the future, where you bolt on generalization by first training a language model, and this will work even in nonverbal domains. So I'm going to switch the presentation tab to an example that we did in robotics, and let me see if I can do that. So I'm going to come back down to earth and talk about a more grounded application of this vision of using language models for nonverbal domains. So I'm going to talk about this recent work we did called BCZ, Zero-Shot Task Generalization with Robotic Imitation Learning, and this is done with colleagues at Google. So in the last 5 or so years, people have been building deep learning systems in the lab that can do tasks in the real world. So our lab built a closed loop, like from pixels only grasping system that can pick up objects. And folks at DeepMind have built things that can stack blocks together, and they can learn single tasks quite well now from raw images. Similar to how like the computer vision revolution just kind of consolidated everything into a single neural network, we're starting to see some work in robotics where we can just fuse everything into a single neural network that does everything. So in the last 3 years or so, I think there's been a large uptick in the number of such projects that can now do multiple tasks. So there's a extension of the grasping work that does multiple tasks. There's transporter networks, and Steven James has this cool task embedded control networks, and many other recent works where like a single neural network is doing multiple tasks. And the work that we did was that we got robots to do tasks they haven't been trained on at all using the real world, trained on at all in the real world. So what we did was we collected a lot of teleoperation demos, like almost like a self-driving car, and then we used language models to confer the generalization to unseen tasks. So let me describe briefly like how that works. Let me skip this slide. This is just describing like kind of the complexity of the data set. But here's a schematic of what's going on. So we have like teleoperators who gather manipulation task demonstrations, similar to how people would drive like a self-driving car and gather data that way. Now we have like a data set with hundreds of tasks, like pick up the cup or push the bowl. And we train a very simple neural network architecture, which is just mapping the observation directly to the action. And also in addition to the observation, you pass in a embedding of language telling the robot what it wants to do. And so we just train this using supervised learning, and it can generalize to unseen tasks because when you give it a new sentence that hasn't been trained on before, the model's still able to understand the sentence and get the policy to do the right things. So here's a diagram of some of the training tasks in blue and then some of the unseen tasks in green. So it can, for example, we trained to place the bottle in the ceramic bowl, and then later we can ask it to place a banana in the ceramic bowl, even though it's actually never done that in the training data. In addition to language, we also study like learning video representations where we have humans use their hands to do the task, and we try to project it to the same space as the language model. So it turns out that we needed to actually align the videos to the same language space in order to get the task generalization capability, which sort of suggests that there's something interesting about the structure of language separately from just training some kind of input modality telling the robot what to do. If you want to get generalization to new tasks, you need to align it in some space that is kind of compatible with the compositional structure of language. And this is similar to what I was saying with my hypothesis that language is the substrate for generalization, not just like a UX method for providing your robot with what to do. Here's a more close-up of the architecture. So, image in, language in over here, and then actions out, and we just train it with behavior cloning. The architecture in the middle is like a ResNet 18, so very simple standard architecture. And so the cool thing is that we get compositional generalization. So in the words used by the language generalization paper was systematicity. So we have an object set here with a series of tasks like place sponge in ceramic bowl. And then we have another set of objects here that, for example, wipe tray with sponge. And these are distinct splits of the training set. So we don't mix the objects between these two sets together during training. We just collect data with these two sets. But at test time, we can combine the objects together into a single scene and then ask it to do a task that it has no demos for. So it was never trained on demos to replace grapes in the ceramic bowl, but because the language is providing the generalization, the robot will just, and the robot has learned to decode language, it'll just do the task correctly. Here's some other examples of held out tasks. As you can see on the bottom, here's an example of a failure as well, where it almost does the task, but it doesn't know how to recover, so it just drops it and doesn't know how to pick it back up and put it in. Very similar to autonomous driving startups, we built a system that lets people take over, and we use like the corrections to provide demos, more demo data for the robot. So the robot does have some capability to recover from mistakes because of this data. Okay, so I want to close out this talk by recapping what I think large language models can do for robotics. So this neural network architecture can do tasks that it wasn't trained on because it generalizes to unseen points in some well-organized task embedding space. And how do you make well-organized task embedding spaces that are conducive to generalization? I think that large language models are the way to go, because the ontology of language is equivalent to the ontology of generalization. Not only can you do compositionality, but I think as we scale these approaches up in the future, you can do more clever things like Chomsky recursion. So for example, maybe you can ask it to execute, like pick up the leftmost object, and it has to reason about what leftmost means. Or you can say like pick up the leftmost object only if it's not close to a red object, and then it would have to be able to handle embedding clauses inside of other clauses, the way that Chomsky says that you can embed an infinite amount of information inside of language. And so in machine learning, we often talk about just like invariance, which is just two different continuous signals meaning the same thing. So all of these are ceramic bowls in our data set, and they should mean the same thing. But if you think about what language can provide on top of that, okay, think about what language can provide on top of that. It's this ability to stitch together meaning in arbitrarily nested ways. And with that, I'd like to open up for any questions. Thank you for listening to me talk about this.
Thank you for your talk, Eric. Any question in the group?
A lot of stuff there.
Any question?
Sure. Eric, how do you see this like scaling up? Like, I've seen lots of models and lots of papers and lots of other work where you're doing simultaneous embeddings, and I totally believe the premise of, hey, text is pretty general, language is pretty general. As long as you co-embed with language, then you can make your other domain at least as general as language. But with RL and robots in particular, like as you were already mentioning, like samples are far and few to come by, they're expensive to go get. So how do you, and I was trying to think throughout your whole presentation, it's like, yeah, I totally believe that like you can get those if there's, data, right? So like OpenAI Clip is just another example of like co-embedding images and text, and really successful, and probably mostly successful just because they have, a huge data set. But that seems like exactly what you don't have here and what you probably won't have for a long time. So I'm kind of wondering like how can you start to collect lots of, is it like watching video games online? Is it like, what are you thinking there? Like what's the path? What are the steps there?
Mm-hmm. Great question. So let me just make sure I replay your question to understand. Understand it. So you're asking like, clip is an example of like being able to get all the sufficient data needed to get the generalization you want. But for something like robotics, which usually it's much more expensive to gather data. How do you scale this up in the long term?
Yeah, robotics and like RL perhaps generally, and just wondering if, because I feel like that's where the cleverness comes in, right? Like, I've seen other examples of like before clip, there like I think Instagram had some paper where they co-embedded, I don't know, tags or captions with photos. And it's like cool, like that, totally get it, right? And it doesn't, like there, I feel like it's less motivated by like whatever architecture, just by like having sheer size of like a data set, which is neat because it has two modalities interacting, images and text. And for robots, like that seems limited. But yeah, no, I think you had exactly the right question.
Okay. So let me answer the pragmatic one, and then let me kind of speculate after the pragmatic answer. So I think for robotics right now, there's like 3 schools of thought of how to scale up robotics. And let me just say robotics instead of reinforcement learning, because that's sort of a harder version of reinforcement learning. One is to do, as you say, like, scrape YouTube videos, scrape Instagram for like, think about like just crawling the internet for like knowledge, right? That's like one approach. And you can imagine that if like internet contains enough knowledge about the world, maybe you don't need so much data to then turn knowledge about the world into behaviors and actions, because it's seen everything, it understands everything. So it's just a small bit of data to connect that understanding to like policy. The second approach is more of like a kind of a tabula rasa, lifelong learning, open-ended evolution approach, which is kind of championed by folks like Jeff Clune at Uber AI, or formerly Uber AI, now OpenAI, where it's like you have these agents that don't need human intervention, but they run in a simulation forever, and they kind of grow in complexity over time, and you get your data that way. And that's like another way to kind of scale up robotics is through autonomous, like basically autonomous self-bootstrapping algorithms. So even if you're not operating a sim, you can imagine like building data collection algorithms where a robot learns to gather its own data and try to solve tasks in some sort of unsupervised way. So this work from like Berkeley, Stanford, and MIT that kind of try to do this sort of thing. And then the third approach is just the brute force thing. So that's something we're doing at Google, where we're just treating it kind of like a self-driving car startup and just collecting the data. And I think a lot of people say that like data collection is hard, but if you compare that to like actually it's data accumulates really quickly if you are careful of what you collect, and you kind of build this flywheel where you add more capabilities on top of existing ones. So like in the past year, we've collected demonstrations of like various manipulation tasks on this large fleet of robots, and we just keep on training on this and incrementally adding to it. And I think like in a few years we'll have enough to do pretty much any manipulation task that is that you could teleoperate on the robot system. So I think like scale looks hard, but someone's got to try it, and it might work. That's another approach. So that's an answer to like how to scale up robotics. Now let me kind of like speculate on what might be possible. So if you take that like language is the substrate of generalization, then maybe you don't need that much robotic data, and maybe what you need more of is language data. And so you could imagine gathering a semi-large data set of robot demonstrations or something, and then you just scale up the number of associated language descriptions that are paired with that data. So this is something that is done in the learning from play paper that I briefly covered. So imagine you describe like the existing robot data you have in as rich of a way as possible. And then now, if you have a joint density over your language, your robot data, you just need to kind of manipulate the language in any way you like, and it'll be able to get the composition of any behavior you want in the robot space. And so you can then just ask it to do whatever you want. And so maybe there's a future where you just scale up language data. That gives you the kind of generalization. And then, of course, you'll probably scrape the internet for this language data. But you get the generalization from language, and then you just kind of bolt it on to the robot data. Does that answer your question?
Yeah, totally. I think a three-part answer definitely answers it. Thanks, Eric.
Any other questions from people online? If not, I'd like to thank Eric to join us for Algo Hour, giving this fabulous talk. And if you have any other questions, please follow up with Eric, who will provide his email to the group. And
Yeah, let me just type in my email right now to the chat.
And Elijah, if you have any closing notes for Eric.
Thank you so much. That was fascinating.
Thanks very much. Yeah, I hope to I'm working on a new blog post that's kind of trying to cover this second part of the talk, and so I'll let you guys know when I publish it.
Thank you so much.
Thanks. Have a great day. Bye.
Have a good one.